Thanks very much for the opportunity to be able to speak here, and I want to lead you through some work that I've been doing about the last 20 odd years or so on denitrifying bioreactors. I like to put this slide up just to remind often my students when I'm talking about nitrogen is that we must remember that 40% of the world's population is supported by food that is grown using nitrogen that we have put onto the land. Okay, so that's you, right? You guys are okay. You guys have got a problem if we don't have nitrogen. So we need to remember that there's a two-sided thing here, right? But the problem is that the system is not entirely efficient, right? So we start losing nitrogen and it starts going to systems where we don't want nitrogen because it causes the same thing, increased growth. So we have a problem then. So we're trying to balance the use of nitrogen. This is my nitrogen cycle. Nitrogen in the atmosphere, that's not doing anything. And then we have nitrogen in ecosystems. We want to get nitrogen out of the atmosphere into our ecosystems to produce growth. We want to hold it here in agricultural systems so that we can produce food. What we don't want is it leaving those agricultural systems and ending up in places we don't want it. When it leaves those systems, we have a nutrient use inefficiency, and what we've got to then do is get it back to the atmosphere. And that's where you need this process of denitrification, right? That converts reactive nitrogen to dinitrogen gas in the atmosphere is what you want. Nitrous oxide is something we'll come to. And this process, denitrification, as was explained earlier on, is controlled by carbon, nitrate and oxygen. Carbon is the energy source, right? Same as us, we have food. They need some sort of carbon support for them, for energy. They need nitrate, that's their equivalent as we have for oxygen, so they use nitrate instead of oxygen. And they need an absence of oxygen because they would prefer to use oxygen rather than nitrate. So if oxygen's around, they start using oxygen and they don't touch the nitrate anymore. So you need a carbon source, you need the nitrate, and you need an absence of oxygen. So this work started for me in the late 80s when I was doing my PhD at this site here. This is an effluent irrigated forest back here. Nitrate concentrations here in these wells was around about 15, 20 milligrams per litre as N. And then down here there was none. It was all gone. So over 2 metres you've got this total nitrate removal. Now the reason for this is that this is wet, so it's anaerobic. There's lots of organic matter in it because it's a wetland. And the nitrate's coming from upslope into this riparian area and being removed. So denitrification can be very fast in small parts of the landscape. Problem is, some of our landscapes look like this, where we've got heavy agriculture up to the edge, wetlands have been drained, we've lost our organic matter, and that sort of natural function has now gone. So I started thinking, what would you do in a system like this? Sure, you can try and restore it, it's going to be 20, 30 years, but let's deconstruct what we need in a riparian zone to make it function. And that's where I came up with this idea in the early 90s, where forget what kind of agriculture, we have cows rather than sheep, mostly now. But you get nitrate coming out the bottom, right, ends up in groundwater. Let's put organic matter into the flow path of that groundwater to enhance denitrification, right? So that was the idea. And I've done stuff in the lab. I can show you that denitrification occurs in the lab, but I don't really care about that anymore. So I dug a trench here downslope of an effluent irrigation site. We got some wood chips, and we mixed it with the soil that we took out of that trench, we put it back in. So you can see that is there now, and we've got wells upslope and downslope and in the well, and you just grass this over. And I built this in 1996. I drove past it the other day. It's still there. Okay, and they're still grazing it. You can only tell by the wells being there. So does it work? This is the data that we collected over the first 5 years of the project. Time along the bottom, nitrate concentration on the y-axis there. The top line is the nitrate coming in, and the bottom line is the nitrate coming out, and I've lifted the zero line up a little bit so you can see it a little bit better. After about 14 years, I had a student come from the States. She wanted a short project, and I said, well, let's see if it's still working. We went back out there, and you can see the nitrate concentrations coming in have dropped, and the reason for that was because they decreased the effluent application, so the nitrogen inputs upslope, but the system is still working. We measured the biogeochemistry of the system, and we could show denitrification was still happening, and there were still particles of sawdust that you could see down below the groundwater at that time. Now, is it still going? I don't know, but 14 years. Other people then started picking this up, trying similar sorts of things. So this Massachusetts, Iowa, around tile drains. Sabine was I've never met her, but awesome honours project where they put a wall in below a feedlot, and then a guy in Florida put one downstream of a plant nursery. And all of these systems were having good nitrate removal. I could show you data, but I'll move on to other systems now. So the concept of putting an organic matter source, a slowly degrading organic matter source, into the path of your nitrate is the general principle. On the left-hand side is the wall idea, the denitrification wall that's installed into groundwater. People then started playing around, and myself, where you take a lined container like this and fill it full of wood chips or bark or whatever, and tie that into an effluent flow, either some sort of wastewater or a tile drainage type system. Just to show you some photos, these are some ones that are treating effluent, so domestic effluent around Taupo. This is Karaka, this is by Auckland. This bed is 150 metres long, 7 metres wide, filled with $70,000 worth of wood chips. And the guy who owns this, after he just heard and talked to us about, he just built this. He talked to us and said, oh, I can build that, and he did. One dairy farm effluent, mind you, there's really high nitrate concentrations. They've got some issues there. And then dairy farm effluent. So it's a kind of a last line of defence. After you've pre-treated your effluent and you're just mostly left with nitrate, then you use these systems. The US started getting pretty interested in this. Some of the early work done by Will Robinson in Canada. This is where they hook it up to a tile drain underneath corn or something, so you've got a point source discharge. And they've built these bioreactors, we call them denitrification beds now. It's just plastic lined, filled with wood chips, and then you put an inlet and outlet structure that allows for bypass flow during high flow events, right? Around Illinois, Indiana, they're around New York as well. So people are putting them in. The Soybean Growers Association are just building them themselves now. So it's gone beyond science research. This is one from Ian Landon, which is just up the way in Palmerston County or Catchment. He's put into the stream itself, and other people have tried this as well. I don't have the data, but he was showing something like a 20% removal in the stream, downslope of Pineapple. Again, this is the kind of data that you get out of this. Time along the bottom axis there, and on the y-axis we have nitrate concentration. Top line is nitrate coming in. Bottom line is nitrate coming out. Okay, so in all of these systems you get removal. It's not fast, and you've got to get the right size to the amount of nitrate that you have, but you get good nitrate removal. And these are all different kinds of systems. This started getting of interest, particularly in the US, like I say, because they have some large issues, particularly in the Mississippi Basin, which extends all the way up into Iowa, Illinois and stuff. And the blue dots are where bioreactors are being put in. This was a joint project I had with the University of Rhode Island. We created a map of these things, and now we're behind because now I've heard that there's something like 50 or 60 in Iowa, and we just don't know where they are because people are just putting them in. The USDA Natural Resource Conservation Service have put out some guidelines, and they fund for them to go in the ground now for farmers. Farmers love it. They get it and they can do it. We then got together as part of that project, Kelly Addy, Art Gold, Laura Christensen, Mark David and myself. We created a meta-analysis, so we went and looked at all the bioreactor results that are out there at the moment and sort of analysed what their performance was and what constrained their ability to operate. I'm not going to go through all of that. There's a paper there if you want it, whatever. Email me if you like. But we looked at what sort of design influence there was, whether softwoods, hardwood mattered, whether temperature was important, nitrate loading, hydraulic retention and age. So all of those kind of things are kind of covered in an initial go anyway, and I can certainly talk to those later on if you want. But I'll just talk about a couple of things first. We've heard this percentage removal thing a few times, and it does my head in. Percentage removals is a very complicated way of thinking about nutrient removal, and I'll just give the example of it here. This is the way I like to think. If you have a load of 20 grams of nitrogen coming in or off a system per day, right, and you put in my case, a wood chip bioreactor, they can remove about 5 grams of nitrogen per cubic metre of wood chips per day. That's about the number, right? So if you put in 20, take away 5, then you end up with 15, you get 25% removal. So is that good or bad? Well, I don't know, it depends on what you want. But if you then stack a bunch of these all up and they're all doing 5 grams per cubic metre of wood chip material per day, you get 100% removal. So when I talk about removal rates in bioreactors, I talk about grams of nitrogen removed per cubic metre of wood chip material per day. You can do the equivalent sort of thing on an aerial basis for wetlands, and we've heard some of that as well. But that's the way I like to try and think about it. So the next few slides, just bear in this, this is the way I'm presenting the data in terms of removal rates, grams per cubic metre per day. One of the things that I often get asked is, what about other forms of carbon? You've used wood chips, but must be other things we can use as well. Stuart Cameron was a PhD student with me. He set up this massive trial, 200-litre containers with different carbon sources and different size fractions, and he ran it with nitrate going through it continuously for 2 years. So a good data set, right? Excellent student. This is what we got out of it, the different carbon sources along the bottom here, nitrate removal rate along the y-axis there, and you can see that basically wood chips like radiata pine is on the slow end. Hardwoods didn't seem to make a whole heck of a lot of difference, so the bugs don't care, hardwood versus softwood. And then you can get into some other things that can certainly crank up your removal rate. So you can go there, but there is a but. Oh, sorry, yes, before I move on. So I was out with Ian Landon looking at some of your sites, and you've got carbon everywhere in your systems. You know, this was pineapple trash, and I've heard there's blanket trash and bagasse. I don't know what bagasse is, but I've been talked about it a lot. And so you've got carbon sources to work with, right? But you do need to think about this carefully. It depends on what you've got available, what it's going to cost, but really how long is it going to last? And the trade-off is that the faster the nitrate removal rate is, the faster or the more frequently you're going to have to replace that material. There needs to be a local context discussion about how often you're going to go back and replace this stuff. That's a discussion really for you in your context. Wood chips, for me, they go slow, but they just sit there and work. How long do they last? We haven't had one run out yet, but what does happen is the rate declines with time. So you might start off at 10 grams per cubic metre per day removal, then it'll go to 5, and then probably to 3, and I think it'll probably stay at 3 or 2 for a long period of time as it just sits there and slowly breaks down and denitrifies. So we have a number of different studies that have looked at these kind of lengths, but at least 10 years, and then possibly longer than that. And then you can just put more in if you want. Issues. We do have issues. This was the second wall that I built. It was in a very deep, coarse sand aquifer. So, you know, metres of sand down. We built a denitrification wall. And what happens when you take a wet sand and you shake it? It compacts. And look at the change in hydraulic conductivity. Went from 65 metres a day to half a metre a day. Expensive mistake. We heard mistakes before. Don't do this. Because it took us ages to figure out where this water was going. Okay. There are places where this is not sensible. Okay. And there are places where it is probably sensible. You guys, from what I can see around here, you have a lot of these kind of clay lenses. And if you can tap down into that, decreasing the hydraulic conductivity to half a metre a day is not a problem. Because it'll still go through that system, right? But it will be context, soil specific. That's stuff that needs to be a local discussion or regional discussion. And I took this photo. I mean, we don't get soils like this in New Zealand, where you've got your sand sitting on the top of a clay. For me, if I could go and have a denitrification wall trial, this is where I would pick. Very neat, and this is near where Ian's working. Other issues, denitrification beds, if you get sediment in them, they clog up. I don't, you know, that's a no-brainer really. This was receiving effluent from that glass house. A lot of fines come out of glass houses, that clogged up. They put some coarser material, gravel at the top end and got rid of that problem. But I'm not trying to pretend that this is, you know, you've got to maintain them a little bit. this first one here, basically they walked away from it and left it for a year and the back end of it clogged up and you've got water running everywhere. It's not, you do have to keep a bit of an eye on these. Nitrous oxide. So we talked about nitrous oxide a lot, and I think it is very important that we talk about this. But I want to put it in this context. If you have nitrate leaving an agricultural system, you've lost it. And it's going to go to the ocean, and at some stage, it's going to be denitrified. And at some stage, you'll get nitrous oxide emissions along that line. If you put a bioreactor in, you will get nitrous oxide from that bioreactor. But it's not whether it occurs or not from the bioreactor, it's the relative amount between these two. Okay. I think that we can look at ways of manipulating the bioreactor to remove or reduce the amount of nitrous oxide that will be produced out of them. My general observation, and this needs to be tested, is if your bioreactor removes all the nitrate, you don't get nitrous oxide. But when you have a bioreactor that is overloaded with very high nitrate concentrations, you get a lot of nitrous oxide. So there's work to be done. So I'm not trying to dodge the issue, but it's there, but it's a relative thing. Costs. This is Laura Christensen led this up. She's an excellent new professor at Illinois. She did a PhD on this, ag engineer. If you ever need anybody to come and talk to you about how to put these in agricultural systems, she's the one, really. She did this kind of cost comparison here. So here's controlled drainage, bioreactors, wetlands, nitrogen fertiliser rate. And then these are things that you do on land, and that scales are different in terms of costs. Now, you could argue about the methodology and how the costs are all calculated and whatever, but what this is saying is this is dollars cost per kilogram of nitrogen removed. And basically, the numbers match up with wetlands. So your bioreactor removal rate is about the same as the cost in a wetland, and less than maybe some of these things that people are doing up on land. This isn't a competition. You guys are talking about treatment trains. I mean, it's a mixed solution, right? But these things are not expensive, basically, is what I'm saying. And the grey is the real cost, and the white is with subsidies or some payment. Right, perfect timing. Lessons learned. So this came out of the meta-analysis, a lot of these conclusions. I'm showing you all this stuff, but you can read up on it if you want. Generally, nitrate removal rates are faster in beds than in walls, and that's often because the beds have got a higher percentage of carbon in them, whereas in walls you'll often have a mixture of carbon and soil. So take that. Wood type doesn't seem to matter, but there are other carbon sources, and you have a trade-off between nitrate removal rate and sustainability. Low nitrate concentrations, they're not going to remove nitrate, generally not an issue, of course, because then you don't need them. Low temperatures will slow things down. Here you guys are well set, you've got high temperatures. Short hydraulic retention times could be an issue. You get a decline in performance with age, you know, this thing starts to settle down, and they're relatively inexpensive. A couple of things that we need to pay attention to. Nitrous oxide emissions, as I've just said. You do get some biological oxygen demand or carbon release when you first start these things up. You need to either pre-wash your product with sawdust or just be aware of that. The most important thing is getting your hydrological connections right. Okay? If the water doesn't go through it, it's not going to work. This is something that I drew a few years ago when I wrote I led a special issue on managing denitrification in systems. And it's just a diagram in here, I guess, showing it's all these different things coming together, right? It's riparian zones, it's wetlands, it's lakes, it's forests, it's industrial treatment plants and bioreactors, and they can be put in different sorts of settings. And what that setting looks like is where the water's going and getting that connectivity. I'd very much like to thank my funding sources that you can see there and a number of my colleagues. I'm particularly appreciative of Ian Landon, who took me out on Wednesday, Peter Grace from Queensland University of Technology, and of course Mike Rowan. Thanks very much, everybody.